All right, in this video, we're going to talk about double integrals and how we can use those to find volumes of solids. For now, we'll find out there's going to be other uses for double integrals, but let's just get started by thinking about, first of all, maybe even just from your 21B, 16B, 17B experience, how do you find the area between two graphs using a single integral? So here we're going to do the area between y equals 4x, y equals x cubed in the first quadrant. So this region here, and you probably want to know where those two graphs intersect. If you set these equal to each other and solve for it, it's pretty easy to see that they're going to intersect when x is 2, and in which case your y value would be 8. So if you recall from any of the previous math courses where you did single integrals, one way to find the area between two curves is to imagine a bunch of very thin rectangles. And for part A, we're going to imagine our rectangles as being really thin vertical rectangles filled throughout this region. And if you recall, an integral is an adding machine. It will add together whatever shape you want it to, as long as you give it a formula for the area of any one of those shapes. And so in a previous math class as a single integral, you may recall to find the area, what we would want to do is add up all of the rectangles whose heights are given by the height of any one of these rectangles is given by the difference between the top function and the bottom function, and then multiply that by the width of one of those rectangles, which is thought of as an infinitely small increment, in this case of x. That width is a tiny little increment of x, which is what we mean by dx. So you may recall that from a previous math class. Again, this gives me the heights, and dx is my infinitely skinny width. So how it changes now, it's not that much different. As a double integral, we can express the same area. Here's how it looks. So we're going to have two integrals. And if we're doing area, we're not going to have anything here. We're just going to have, and if it's vertical cross sections, vertical rectangles, we're going to go dy dx. And the way it works is there's sort of, we don't usually put this, but there's an invisible set of brackets here. And the inside integral goes first. And so what we put for the here, I'm just going to do this one. For the top limit here, it's like, what function does my rectangles hit on the top? They hit y equals 4x. What do they hit on the bottom? Y equals x cubed. And what is that true from in terms of x? That's true from x equals 0 to 2. In other words, I want to add up all of those rectangles from x equals 0 to x equals 2. So let me show you why that comes out to be the same. So like I said, you don't put anything here, although if it helps, you can imagine a little invisible 1 there. And so to work this out, you would start at the inside and ask yourself, what's the antiderivative of 1 with respect to y? And that would just be y. So this outside integral would stay there. It would be from 0 to 2. And then we would have y evaluated from y equals 4x to y equals x cubed. And we'll integrate that result with respect to x. If I put in the top limit minus the bottom limit, I end up getting 4x minus x cubed dx, which you can probably recognize that's exactly the setup we would have used if we had done this as a single integral, top minus bottom dx. We'll finish this one off. So that's going to integrate to 2x squared minus x to the 4th over 4. So 8 minus 4. And of course, if you plug in 0, it's 0 minus 0. So it looks like my final answer is 4 for my area. So to review, for the double integral here, you're just going to put your top function. If you're using vertical cross sections, your inside integral, this is going to be what your thin rectangles hit on the top. This is what they hit on the bottom. And then the outside limits are just the same as you would set them up if you were doing a single integral. Now you may recall in single integral calculus that you can also, if you want to, describe an area using horizontal cross sections or horizontal rectangles. So same figure here. This intersection was 2, 8. But now we're going to imagine filling this region up with a bunch of thin horizontal rectangles throughout the region. And let's just go straight to the double integral. So if we're setting this up as a double integral, what happens now is the inside integral is going to be integrated with respect to x. So we'll put our invisible brackets here. And the outside integral will be integrated with respect to y. So there's one big change there. If you're doing horizontal cross sections, the orientation is going to be dx dy. And if I go back up to the other one, if we're doing vertical cross sections, it's always going to be dy dx. So that's a good thing to know with double integrals. Now, if you recall from, if you were doing this as a single integral, instead of top minus bottom, what we would do is we would go right minus left. So every rectangle that I draw in here, what does it hit on the right? It hits y equals x cubed, but I have to write this in terms of x. So in terms of x, that's the same thing as x equals the cube root of y, or y to the 1/3, right? If you solve that for x, I'll go y to the 1/3. And what did they hit on the left? They hit my y equals 4x, also known as x equals 1/4 y. And that's true as long as my y values are between what two numbers? My lowest rectangle is at y equals 0. My highest one is at 8. So those would be my bounds on the outside. And if you work this out, you would get the same answer in theory, but hopefully you could try that on your own. But again, to emphasize, for horizontal, this limit is always going to be what my rectangles hit on the right. This is going to be my left. Okay, so let's try this backwards now. So say I had this double integral. That integral represents the area of some region. And so we want to sketch the region of integration that this integral is having us find the area of, right? So the first thing I would look at is I would notice that this integral was written dy dx. So that tells me this region was described using vertical rectangles, because it's dy dx. And so then I know with vertical rectangles, it's always top minus bottom. Oftentimes they write the limits here. They don't indicate which variable, but remember that the inside one in this case, these are y. This is y equals 9, y equals x squared. In my region of integration, this is what my rectangles hit on the top. This is what they hit on the bottom. So I've got a pretty good starting point here. Then I could sketch y equals 9 is a horizontal line. Y equals x squared is a parabola. The vertex at the origin. So that would certainly work. I could imagine rectangles that hit y equals 9 on the top, y equals x squared on the bottom. But I also have to pay attention to my outside limits because this says I want to keep my x values between 0 and 3. And you'll notice that y equals x squared and y equals 9 actually intersect. This point right here would be 3, 9. So because my limits are from 0 to 3, that means the leftmost rectangle I want is the one that's right here, right at x equals 0. And the furthest one would be right here at x equals 3. So my region of integration would just be this right here, just this region right here. Not this half, because this half would stretch over here to -3, but that's not what I had in my double integral. And here's a good skill to be able to do. We'll see this in a little bit here. Now that I've sketched my region of integration, what I want to do is reverse the order of integration, meaning the original integral was, the order was dy and then dx. So what this means, I want to switch to dx dy. So I want my integral like this. And what almost will never be true unless you get something with just constants. You would like to think, well, if this is x and these are y, and I switch it to dx dy, why don't I just put the x limits here and these y limits there? It's not going to work. Because what you have to think about is this region of integration. I think I'm going to redraw it. Let's move this down. Now that we know our region of integration was, here was y equals 9, here was y equals x squared. Recall that this would be 3, 9. Our region of integration was just this part right here from the what we did up above. But now I'm switching to horizontal rectangles. So if I imagine filling this region up with a bunch of thin horizontal rectangles, what does every horizontal rectangle hit on the right? Y equals x squared, also known as x equals square root of y. So that would go up here. What do they hit on the left? Well, they hit the y-axis, which is the equation x equals 0. And that's true as long as my y values are between what two numbers? Well, my lowest one's at 0. My highest one would be right there at 9. The outside limits of integration should always be numbers. They shouldn't be functions, or it's not going to give you area. Okay, so you should practice plenty of those if you've got examples to do that, but let's move on a little bit to what good, why would I care about double integrals if we can just use a single integral, right? For both of those, I didn't need to use a double integral. I could have described that with a single integral. Why do we want to have double integrals? Well, with a double integral, we can actually calculate the volume of a solid that is not necessarily something that was revolved around the axis. If you recall from previous calculus courses, if you took a region and spun it around the x-axis, you might be able to use the disk or washer method to calculate the volume of a solid. But they have to, for those types of volumes, they had to be revolved around an axis. Now we can have the ability to imagine a solid. So let's look at our first example. In the first octant, remember the first octant is in the three-dimensional graphing system where x, y, and z are all positive. There's 8 octants, but only one where x, y, and z are all positive. And it's bounded above by z equals 6 minus y and below by the square region. X is between 0 and 2 and y is between 0 and 2. I went ahead and drew the picture so I'd get a nice picture for the video here, but let's describe let's remember how we graph things in 3D. Z equals 6 minus y only has 2 variables, and you can think of that as a linear function in the YZ plane. That would be like a line with a z-intercept of 6 and a slope of -1. So that's this line right here. I started to draw it. It's going down. And recall how it works if one of the variables is missing in an equation, like in this case, x, you can imagine taking this line and extending it in the x direction. Both with directions, technically, into the paper and out of the paper, but we're going to extend it outwards. So you can imagine sort of a flat, not a flat, a slanted plane here that's kind of sloping downward. Now, the solid that we're describing, the image I like to use is that of a room. If you're sitting in a room right now, you probably have a square or a rectangular floor. So that's kind of like the bottom here. This is describing the floor of the room. And this z equals 6 minus y is kind of like the ceiling of the room. The ceiling of the room I'm in has a horizontal plane at the top, but this one's kind of slanting down. So think of this as the ceiling. And so ultimately, we're trying to find the volume of a room where this is the floor and this is the ceiling, and you have walls going straight up from the floor until it meets the ceiling. So how we do this is kind of like finding area where we were imagining a bunch of thin rectangles under our curve. For this solid, I already drew this, but you can imagine, if you can imagine dividing the floor up into a grid, technically with infinitely small squares, but I wanted you to see this. And over every single small square here, you can imagine not a rectangle, but a column, a rectangular column that's stretching up from the floor until it hits the ceiling. And if you can imagine a whole bunch of those drawn throughout the region, I could draw another one here. And if I had a way to find the volume of all of these columns, draw one here. If you can picture all these columns throughout here, finding the volume of all of those columns is going to essentially give me the volume under this ceiling, but over this floor, right? They're all going to have different heights. So in the same spirit as a area problem, if I can find a formula for one of these columns, so let's take one of them, it's going to look like this. How would I find the volume of a column like this? Well, the height of my column would be essentially given by, remember, z could also be thought of as f of xy. So the height of my column would be my z value, or f of xy. And what is my length and width? Well, one of them is a small little increment of y, the other one's a small little increment of x. So it's dy dx. So the volume of a column is length times width times height. We'll put the height first. It's f of xy dy dx. And just like we've seen with single integral calculus, if I can integrate, if the integral is like an adding machine, if I integrate this, I can find the volume of all of these columns throughout this region. But because I'm integrating over an area, I'm going to put a double integral. And the notation we usually use is we put an R there. R is like the floor. R is the floor. So here is my general formula for finding the volume under a curve. Now, what can change, of course, is when you do volume, it's height times length times width, but it doesn't, the order of multiplication doesn't matter. So these could be reversed, right? It could be f of xy dx dy. It just depends on how you want to set up your integral. So here's how it's going to look for us. Because my floor for my bounds for x and y, it's just y goes from 0 to 2, x goes from 0 to 2, which are just constants. It doesn't really matter. So I'm just going to integrate f of xy, which is 6 minus y. That's giving me the heights of any one of those columns. And I'm going to do it dy dx, but you could do it with dx dy as well. And again, x is varying from 0 to 2, y is varying from 0 to 2. So for both of these, y is going from 0 to 2, and so is x. So to calculate this, I'll find my antiderivative of this with respect to y, which is 6y minus y squared over 2, evaluated from 2 to 0. If I plug in 2, that's going to give me 12 minus 2, so 10. And then, of course, if I plug in 0, I get nothing. So then this is just going to be the integral from 0 to 2 of 10 dx, which integrates to 10x from 2 to 0. If I plug in the 2, I get 20 minus, if I plug in the 0, I get nothing. So the answer is 20. So let's try another one. This one's one of my favorite ones. We're going to find the volume of the solid in the first octant bounded by x plus y plus z equals 1, which is also a plane. How do I know? It's because all three of my variables are to the first power, so I know that is an equation of a plane. But unlike the one we did here, which was also a plane, z equals 6 minus y was a plane, but my strategy for graphing that was to just imagine sketching the line and extending it in the x direction because x was missing. For this one, since I have all three of my variables, this isn't going to be like a line extended in a certain direction. It's still a plane, but it's not, I'm not going to graph it the same way. So the way I'm going to graph this one is noting that just like to graph a line, all you really need is 2 points and there's one line going through it. To graph a plane, I just need 3 points on my plane, and there's only one plane that will connect those 3 points. And the easiest way to graph it is to think about my intercepts. My x-intercept is what happens when I let, no, not x equal to 0, is what happens when I let y and z both equal to 0. And if y and z both are equal to 0, I get 1. My y-intercept, if I let x and z be 0, is also 1. And my z-intercept is 0, 0, 1. So 1 on the x-axis, 1 on the y-axis, 1 on the z-axis. And if I connect those with straight lines, hopefully you can see a triangle, but it's a flat surface, isn't it? That's a flat surface. And a lot of people, when they think of, if you say it's a plane, they get a picture of a rectangle. Well, remember, a plane goes in all directions forever, so it really doesn't even have the shape of a rectangle. What we're seeing is the portion of this plane that actually intersects the first octant, right? So it keeps going. So sometimes when I'm graphing, I draw like little arrows to say that keeps going down, this keeps going that way, this keeps going that way. We're just looking at this portion. And if it's the solid is strictly in the first octant, then you can hopefully see that I'm going to treat this plane as my ceiling. There we go. And the floor of the room is this bottom triangle right here. This is what we call R. That's this bottom triangle here. That's the ceiling, that's the floor, and you've got some walls there. Now, one of the reasons I like this problem, I'm going to take a little side note here, is one way to think of this solid, which is maybe kind of an interesting thing, is I drew here just separately a cube, a unit cube, and so a cube that intersects the x, y, and z axis at 1. And my plane is actually, remember we had z-intercept of 1, x-intercept of 1, and a y-intercept of 1. So if you can imagine our solid is being bounded by this, it's a little hard to imagine, but one way I thought about this was that if you can picture this as a little puzzle, maybe you've seen some puzzles that kids make that come in the shape of a cube, but you pull it apart, it's a bunch of different shapes. And try to imagine that pink solid, which is what we're going to find the volume of, as one of the puzzle pieces of this cube. And remember, the volume of the cube, it's a unit cube, right? It's 1 by 1 by 1, so the volume is 1. So clearly the volume of this pink shape is something smaller than 1. It's a fraction. And an interesting thing to ask yourself is how many of these, if you think of this pink thing as a puzzle piece, how many of those by volume? I don't know that they would necessarily fit perfectly in, but if you melted it down, how many shapes like this could fit inside that cube? And some common answers I would think are maybe 3, maybe 4. And when we answer our question, we're going to be able to answer that. And the answer might surprise you a little bit. Anyhow, back to this. So to find the volume, what I sometimes do, because I'm going to have to put limits of integration on my double integral for the region of the floor. So sometimes it's helpful to just sketch the floor separately. Like it's always in the XY plane here. So my floor is really this triangle right here. And notice that that triangle hits the x-axis at 1, 0 and hits the y-axis at 0, 1. And so this is R right here. I'm going to probably need the equation of this line right here. There's a couple of ways you could do it. One of them, if you just think y equals mx plus b, what is the slope of this line? Well, to get from here to here, you go down 1 over 1. So I know it has a slope of -1. So it's negative x plus your y-intercept, and my y-intercept is 1. So that's the equation of my line. Another way you can get the equation of the line, by the way, this line, which is what this is also part of my plane. And if you think about it, this line represents all of the point on my plane equation where z is equal to 0, right? This line right here is z equals 0. And if I set z equal to 0 and solve for y, I get y equals -x plus 1. Okay, so my volume, double integral, kind of my default unless I have a good reason to switch it up, is I'll usually stick with dy dx, because again, what dy dx means is I'm going to describe this, describe R using vertical rectangles. So my pen is running out. So f of xy is really z. So I actually have to go up here and solve for z. Z is equal to 1 minus x minus y. That's f of xy. And now I have to put limits of integration using vertical rectangles. So now I'm just focused on the floor. And using vertical rectangles, just like I started this video, if you imagine putting vertical rectangles in here, what does every vertical rectangle hit on the top? It hits y equals -x plus 1. What does it hit on the bottom? It hits y equals 0. And that's true as long as my x values are between 0 and 1. So there's the setup. Let's actually work this out. So I want to integrate this with respect to y first. So the antiderivative of 1 would be y. We're treating x as a constant, so the antiderivative of -x is actually -xy, right? It's not like a partial derivative, it's an integration. And then that would be -1/2 y squared. Evaluated from y equals -x plus 1 to y equals 0, and then we're going to integrate all of that with respect to x. put that in for my y's. Negative x plus 1 minus x times negative x plus 1 minus 1/2, negative x plus 1 squared. Let's distribute. Plus x squared minus x. Let's FOIL this out first. That's going to come out to be x squared minus 2x plus 1. Maybe we can combine a couple of things. If we combine that term and that term, and maybe the 1 minus the 1/2. So the 1 minus the 1/2 is 1/2 minus 2x plus, oh, whoa, 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 whoa. I combine that and I have to distribute that, don't I? Let's try not, maybe I won't simplify yet. So this is going to be negative x plus 1 plus x squared minus x minus 1/2 x squared. This times negative 2x is plus x minus 1/2. There we go. Now I'll combine some like terms. X squared minus 1/2 x squared is 1/2 x squared. Negative x minus x plus x, so that actually cancels with one of those, so it's just minus x. And then 1 minus 1/2 is plus 1/2. Almost there. If I integrate this, x cubed over 3, I'll get 1/6 x cubed minus x squared over 2 plus 1/2 x from 1 to 0 gives me 1/6 minus 1/2 plus 1/2. And of course, if I plug in the 0, I get 0 for all of them. So my final answer is actually 1/6. So let's take this back to what I posed at the beginning. What that's saying, remember that this shape that we just found the volume of can be thought of as part of this cube that has a volume of 1. And we got 1/6 for the volume of the pink region, which means you could fit 6 of those pink volume puzzle pieces into this cube, at least volume-wise, which I don't know about you, but that's more than I would have suspected, right? Kind of an interesting result. Okay. Last idea, but I got a couple examples for this. Now that we know, okay, so the way it works, you've seen hopefully throughout the video, reviewing here, if starting at like one of the ones, number 2 here, if you're doing a double integral where there's no function there, and then you can just think of it as a 1, you're really finding area, right? You're finding area. But if you have something sitting here, like we just did the last couple examples, then this could be thought of as the volume of a solid. So in this problem, we're not asked to sketch the volume or anything. Somebody has written an integral, presumably for the volume of some solid, and they're just asking us to evaluate it. So what would be required here to evaluate this is I would have to first find my antiderivative of e to the x squared with respect to x, right? That's what I'd have to do first. And this is difficult to know, I know, as a student, because, you know, even if you just did a course with integrals and you learned all your techniques like U substitution, integration by parts, partial fractions, it's not always evident that there are integrals that actually cannot be done. This particular integral, you cannot integrate e to the x squared with respect to x. This isn't a proof of why that's true, but the only thing I could think of if I was going to try to integrate e to the x squared with respect to x is I would maybe try letting u equal x squared, and then du would be 2x dx. And if you recall with u substitution, I can get away with the constant not being there, but in order for u substitution to work, I would at least have to see an x dx. And I don't have an x. So I know that u sub isn't going to work. The other maybe candidate you might have been thinking of is integration by parts. And you can try it if you want to, but I can tell you it's already well known that this integral, there is no way to integrate e to the x squared with respect to x. So how am I going to proceed? Well, I can't integrate e to the x squared with respect to x, but I could integrate e to the x squared with respect to y, because then I'd be treating x as a constant, and all of this would be a constant. So what we need to do on this integral is reverse the order of integration, which we did earlier. I need to make this a dy dx integral. And as you hopefully picked up on the previous example, I can't just switch these around and then just switch these limits around. It doesn't work that way. So in order to reverse the order of integration, what I first need to do is sketch the region of integration that the integral was written with. Sketch region of integration. And for the region of integration, it's all about this and this. Whoops, and this. Don't worry about e to the x squared. That has nothing to do with the region of integration. That's what we're integrating, so you don't have to worry about that. So if you look at this, we can see that because the integral was dx dy, we know that the region of integration was written using horizontal cross sections. We know that these are x limits. These are y limits. And if you go back to horizontal cross sections, we know that this is what my rectangles should hit on the right. This is what they should hit on the left. Let's sketch that out. X equals 1 is just a vertical line. X equals 1/2 y. If that gives you trouble, notice that x equals 1/2 y is the same thing as y equals 2x if you solve it for y. That's just a line with a fairly steep slope like this. And I can now kind of imagine some rectangles that are hitting this on the right, this on the left. So there's one rectangle. And now let's check to make sure what our bounds for y are. This says our lowest rectangle should be y equals 0. Well, that kind of makes sense. That's right here at the bottom of this triangle. And the highest one should be at y equals 2. But notice this point right here, if you plug in 1 for x, that point is y equals 2. So my highest one is right there. So in other words, this triangle is my region of integration. And now that we know that, what we want to do is reverse it. So if I were to take this region of integration and now imagine filling it up with a bunch of thin vertical rectangles. Pen's not working so well. There we go. Vertical rectangles. So we're going dy dx. What should go here is what every vertical rectangle hits on the top in terms of y. Would that be y equals 2x? On the bottom, they always hit y equals 0. And that's true as long as my x values are between 0 and 1. And then you can just put your function back in there. So again, notice that these limits, new limits, are not what you would have gotten if you just reversed those, right? You absolutely, in order to reverse the order of integration, you need to sketch the region of integration from your original integral first, and then use, in this case, vertical rectangles to get your new limits. If I knew a faster way, I would tell you, I promise you, but this is the only way to do it. Okay, so now let's see why this is better. As we said, the integral of e to the x squared with respect to y, since I'm treating this as a constant, that would just be e to the x squared times y, evaluated from y equals 2x to y equals 0. And notice when I plug that in, of course, I'm going to get 0 there. I get 2x, which is perfect if you go back to the idea of u substitution, because I tried to let u equal x squared and I didn't have my du. Now I have it perfectly, right? I have a 2x dx right here. So this is really just the integral of e to the u du, which is e to the u, or in this case, just e to the x squared. So I'm going to get e to the x squared evaluated from 1 to 0. E to the 1 minus e to the 0. E to the 0 is just 1. So this integral has a value of e minus 1. A question you're probably wondering, which is a very good question, is how do I know if I'm going to have to reverse the order of integration? Hopefully they will tell you, they will say, evaluate this integral, note that you have to reverse the order of integration before you do evaluate the integral. If they don't tell you that, which is the worst case scenario, then what I would recommend is, if you get asked to evaluate an integral, you've got to integrate this one with respect to y. I've got some y terms in the bottom. And if, this one, I'm thinking if I tried to do a u substitution, in this case, du is equal to 4y cubed dy. And constants are okay, but I'm missing this, right? I would absolutely need to see a y cubed somewhere in the numerator in order for this to work out. So what I would say is if you try a u substitution and you're just not getting the du that you need to make it work, it probably means that you cannot integrate this with respect to y. So you're going to need to reverse the order of integration. Try reversing the order. The other thing too is if it turns out that maybe there was some way of integrating it and you just didn't see it, well, if you reverse the order of integration and get a new integral and can evaluate that, it's going to be the same anyhow, right? So that doesn't hurt to reverse the order of integration. Okay, so to do that, remember you want to sketch the region of integration first so that you can see the area we're dealing with. You may want to pause the video and take a minute to sketch out the region and try to reverse the order of integration on your own. Okay, so then this time, because it was dy dx, I know that my region of integration was written using vertical rectangles. So I know y equals 8 is my top function, y equals x cubed is my bottom function. I know y equals 8 is a horizontal line. Y equals x cubed goes to the origin like this. And so I can picture some rectangles, top to bottom. Now let's check out my limits for x. This says I want to keep my x values between x equals 0, which is right along the y-axis here, and x equals 2, which just happens to be where these two graphs intersect, right? That's 2, 8. So my last rectangle is right here. So this is my region of integration. That's what we call R sometimes. Now that we know R, you want to switch your integral to dx dy, so maybe pause the video again and see if you can describe this region with horizontal cross sections. Still going to be the same function, so 9x to the 8 over 1 plus y to the 4th, but now I want to write it as dx dy. If I fill up this region with horizontal rectangles, what does every horizontal rectangle hit on the right? It hits y equals x cubed, also known as x equals the cube root of y, or y to the 1/3. What do they hit on the left? They hit x equals 0. And that's true as long as y is from 0 to 8. All right, so let's finish this off. Hopefully this will work out here. So now I'm integrating with respect to x, which means I'm treating y as a constant. So in fact, if it helps, if I'm treating y as a constant, that means this whole denominator is constant. I can actually factor that out of the integral, at least the first integral, and just worry about integrating 9x to the 8th. And the antiderivative of that is 9x to the 9th over 9, so it's just x to the 9th. Evaluated from x equals y to the 1/3 to x equals 0. But if I plug in y to the 1/3 and raise it to the 9th power, this is going to turn out to be y cubed. And then, of course, if I plug in 0, I get nothing. So when all is said and done, this will turn out to y cubed. And now let's go back and try the idea of u substitution. If I let u equal 1 plus y to the 4th, du is 4y cubed dy. And the way I do my u substitution, I really want to see a 4y cubed dy, but I'm missing the 4, so I call this the wishing method. I'm going to wish for a 4 right there, compensate outside the integral with a 1/4, because 4 times 1/4 is just 1. The 1/4 will stay there, and this is now 1 over u, and all of that is now du. So my antiderivative is ln of u, oh yeah, or ln of 1 plus y to the 4th, evaluated from 8 to 0. I have no idea what 1 plus 8 to the 4th is. It's a very big number, but I do know if you plug in 0 for y that the ln of 1 is 0. So this should be my final answer. All right, hopefully this helps. Got to get pretty good at double integrals, and it only gets worse because after double integrals, we get into triple integrals. More fun, right? Okay. Thanks for watching.